Hello everyone, this is Ms. Page. In this lesson, we are going to talk about a method for graphing rational functions that we consider more complex, meaning that they are not functions that we can graph using our transformation format. We graphed some where we rewrote the form first. Those can be graphed this way also. But the ones where in the first lesson of graphing where we had plus or minus with a k value after the ratio, I want you to realize and understand that those we cannot graph using the method in this lesson. When there's a plus or minus k value at the end that we can identify, we have to use transformations, or transformations would be the easiest way to graph those. So now what I'm going to look at here is this is the form of our rational functions. So what I was saying is that you can't have a plus k after that. If you have a plus k after that, then you would have to use transformations or get a common denominator, all kinds of stuff. So we're going to look at ones that are in the ratio format in this lesson. And a super important thing is to realize that for much of the graphing process, you need what we call the reduced or simplified function. So if there are any common factors between the numerator and denominator, specifically factors that involve your variable such as x, then you need them reduced out, simplified down to a ratio of 1, and that's what this is saying right here. We need to reduce that function and find its simplest form. Only then are we going to be able to accurately find all of the key features that we need to graph. And specifically, when you can, not all of these functions will reduce, keep that in mind, but when they do reduce, when there is a common factor between the numerator and the denominator, then it's that reduced factor or that matching factor that is going to enable us to find the coordinates of any holes in the graph. Holes, remember, are points of discontinuity, so they create an undefined ratio, but they don't create an undefined ratio in terms of an asymptote, in terms of a hole. And so a key thing to remember when you are looking at this step of finding the coordinates of any hole, that what you do is you focus on the reduced factor. The one that went away, that is the one that we're going to use in order to help us find the x coordinate of the hole. Then we will use the reduced form of the function to find vertical and horizontal asymptotes. We'll look at zeros and we'll graph zeros if there is a zero and if it's reasonable to graph it given the grid that we're working with. Same thing for the y-intercept, if it's reasonable to graph the y-intercept. These are good points. So remember, when we graphed using transformations, we used 1, 1 and negative 1, negative 1, and then we transformed those key points, and then we had a point for each of the pieces of the graph. With the more complex ones, there's a larger variety of what can happen, and we use as many of the points as we can, such as zeros and intercepts and holes, to help us to get an accurate picture of the graph of the function. If we have to, then we will choose an x and plug it into the function to calculate a y to get other points as needed. And that's what this is saying. So we know to graph asymptotes is dashed lines, graph any intercepts, which would include both x and y intercepts, x-intercepts being our zeros, and graph enough other points, if necessarily, so that we can graph or sketch each piece of the curve. All right, let's take a look. So here is our first example. We're looking here at just graphing in this lesson, graphing this rational function f of x. So like I said, super important that we realize the first thing we want to do is find the simplest form of this function. So what we would want to do is factor both the numerator and the denominator of this function. So I'm looking at factoring here, and this would be a 2x and an x, and here I'm going to have to, use my knowledge of the numbers and guess and check. So let's see, I think we are looking at a -3 and a +3. That'll give us a -6 plus 3, which would be -3x for our middle and a -9 for the end. And then here we're looking at x -3 and x + 2. And so we can see that x minus 3 is a common factor, and it's going to reduce to 1. So the simplified or reduced form of our function becomes f of x equals 2x plus 3 over x plus 2. Now, here's what people tend to get confused on, so be careful. When I go to figure out if there's a hole when and only when I had a factor reduce. And that factor that reduced out, that went away, that common factor, that is going to allow us to get the x coordinate of our hole. So we want to know, well, where is x minus 3, that expression that was reduced, equal to 0? And it's equal to 0 at an x value of 3. Well, that 3, ladies and gentlemen, is the x coordinate of the hole. Now, to get the y coordinate of the hole, we simply evaluate our reduced function for x equals 3. So we're going to plug in 3 here and here, do the math, and that will be the y coordinate of the hole. So we'd have 2 times 3 plus a 3 over 3 plus 2. That's 6 plus 3, which is 9 over 5, 9/5, or 1 4/5, or 1.8 if you prefer. So there's the coordinates of the hole, and that's going to be a point of discontinuity for this function. Now I need to now look at asymptotes. So my asymptotes, vertical asymptotes, remember I'm using now, again, my reduced function here. And my denominator, x plus 2, I'm going to have a vertical asymptote where that denominator is equal to 0. That is also equivalent to where x plus 2 equals 0. And if I subtract 2, it gives me x equals negative 2. This is the equation of our vertical asymptote, x equals negative 2. The horizontal asymptote, as we learned in a previous lesson, what we can do is take, assuming that our numerator and denominator are both in standard form, which they are here, we would take the ratio of those first terms in the numerator and the denominator. And that would be what we'd look at for a horizontal, y equals 2x over x. And that is going to reduce to just y equals 2. All right, there's our asymptotes. So now we can look at 0 and we can look at y-intercept if those are nice points to do. Our 0, we're looking at if y, or f of x, is 0, which gives us this little equation. Multiplying both sides by x plus 2, that's going to just give us 0 equals 2x plus 3. And subtracting 3 and dividing by 2 gives us a 0, where x is equal to negative 3/2 or negative 1.5. The y-intercept, remember, is when x is 0. So that's f of 0. And that would be then 0 plus 3 over 0 plus 2, which is a positive 3/2. So this gives us the point negative 1.5, comma 0. And this gives us the point 0, comma positive 1.5. Those will all be nice points for us to include in our graph to get the best picture we can, and hopefully we'll get points on each piece, but that doesn't always happen. So let's take a look now. I'm going to draw my axes. And let's see, I kind of keep in mind where my asymptotes are. Those are my translations. Couldn't actually see them from the beginning, but now I know I've got this translation to the left 2 and up 2. So I might want to push my y-axis a little bit to the right and move my x-axis perhaps up a little bit. Then graphing my asymptotes at y equals 2, which is here. Oh, I probably should have gone down. I wonder, am I going to be okay? Yeah, I'll be all right. Should have gone down there instead of up. And then x equals negative 2. That's going to be here. That's not very good. That's better. And now what I'm going to do is I'm going to draw an open circle at the coordinates of the hole, 3, 1 and 4/5. So here's where x is 3. This is 1 4/5 is right about there, say. And so that is going to give me, that's where the hole is. Then I've graphed that. I've graphed my asymptotes. I'm going to graph the 0, which is at negative 1.5, 0. So here's negative 1, here's negative 1.5, so it's actually here. And then I'm going to graph my y-intercept, which is at 0, positive 1.5, which is here. Now what I should realize is that all three of these points, well, the 2 points in the hole, they're all in the same section of the graph down here in this bottom right corner. They all belong to the same piece. So my curve for this right side piece goes through all of those and then heads towards the asymptotes, towards the ends. So what does that mean? Well, that actually means that I need to figure out at least one point for this left side over here. Where is my graph? And the only way I really have, or maybe not the only way, but at least the easiest way, is generally to pick an x value from this part of the domain and then plug it into our reduced function, find the y that goes with it, and then graph that particular point. So I would pick an x value closest to my vertical asymptote, so that would be, say, negative 3. And that's usually one of the easiest ones to work with, especially if you are not able or allowed to use a calculator. So I'm going to look at what happens in my reduced function if x is negative 3. That's going to give me, so I'm looking at f of negative 3, which would be 2 times negative 3 plus 3 over negative 3 plus 2. That's negative 6 plus 3, which is negative 3. Negative 3 plus 2 is negative 1, which is positive 3. So this gives me the point negative 3, 3. So I'm going to graph that point, negative 3, 3. That puts it right there, and that gives me a point for this piece of my function to finish it up. All right, moving on. We have a second example. This one does have differences, but it also does have some similarities. So what I'm looking at here, here's my function f of x. Again, with these more complex functions, you really do have to remember before you start jumping in and trying to figure out any of the points or the asymptotes that you make sure it is in simplified or reduced form. So we want to look at factoring as much as possible to see if we have common factors. So this denominator factors into x minus 3 and x minus 1. So x minus 1 is a common factor between numerator and denominator, and they will reduce to 1. Be super careful here. I often see mistakes here with people misunderstanding that, this x minus 3 that's left is in the denominator, and so it does have to stay there. So our reduced function becomes f of x equals 1 over x minus 3. All right, so now I'm looking at the whole, which it does have one because I had a reduced factor up here, my x minus 1. And so that whole, its x coordinate is going to be where x minus 1 is equal to 0. And adding 1 to both sides, that gives me x equals 1. So, as we said, that is the x coordinate of this whole. To find the y coordinate of this whole, what we need to do is take our 1 and evaluate our function, our reduced function right here. So that's going to give us that f of 1 is going to be 1 over 1 minus 3, and that's a negative 2, so that's a negative 1/2. There's the whole. Going to be a point of discontinuity, an open circle at that location. Then I'm going to find my asymptotes. And so again, my vertical asymptote, I'm looking again, always now focusing here on my reduced or simplified function, where my denominator would be equal to 0. My denominator is x minus 3. Where is that equal to 0? So again, you can see if we add 3 to both sides, that gives us x equals 3. So there's our vertical asymptote. And our horizontal asymptote, we are going to take and look at the ratio of the first terms. So that would be 1, because that's the only term in the numerator, and x. We're looking at 1 over x. And this actually doesn't reduce down to a number value. It continues because we can't get rid of the x this time. So this actually tells us, remember, that y equals 0. is our horizontal asymptote. And we learned that in a previous lesson too. All right, so now I'm going to take a look at my 0 and y-intercept. So finding my 0, my f of x value or y value is 0. That gives me 0 equals 1 over x minus 3. Multiplying both sides of this equation by x minus 3, I get 0 equals 1, which is a false statement that doesn't involve x, which means there is no 0. Don't have that one this time. Looking at my y-intercept, that occurs when x is 0. And again, I'm using my reduced function here, so I get 1 over 0 minus 3, so that's negative 1/3. So I do have a y-intercept at 0, negative 1/3. All right, so now I am going to look at drawing my axes. And so I have x equals 3, so I might want to move my x-axis a little bit to the left just to make sure I have enough room over there on the right side of it. And y equals 0 is my x-axis, so it can be in the middle. And then I'm going to draw a dashed line at x equals 3 for that asymptote. And then you can draw a dashed line at y equals 0, which is your x-axis for that asymptote, or not. That's optional because your axis can act as your asymptote. We just have to draw the curve correctly. All right, so now I'm going to go back to the other characteristics. And I'm going to graph the whole. And so the whole is at positive 1. 1 is here, negative 1/2. So it would be, get rid of that because it's kind of in my way, right there. I'm going to make sure that's an open circle. So I just did the whole. And then I have no 0, but I do have a y-intercept at 0, negative 1/3. Now negative 1/3, remember, is actually larger than negative 1/2. So that puts this point right about there. So this point, our y-intercept and our whole are both on the same piece of the curve, and we're going towards our x-axis. Y equals 0 is an asymptote, and then we're heading down here towards the vertical asymptote on that side. And that's all that our key points give us. So we need to, as we did in the previous problem, find a point for the piece of the curve that's over here on the right side. And so the way to do that is to pick an x value that's in this part of our domain and then plug that into our reduced function to find its y value. So that's what we're going to do now. So I would pick the whole number close, or the integer rather, probably closest to my asymptote, which would be positive 4. That's what I would use for x. So I'm going to find f of 4. And f of 4 would be 1 over 4 minus 3. 4 minus 3 is 1. 1 over 1 gives me equal to 1. So that gives me the point 4, 1. See how nice and easy that was? So 4, 1 would be right there. Or maybe I should put it in blue like the other. And then I can draw this piece of the curve like so. And that finishes up this problem. All right, moving on. So here we have a practice problem. I encourage you to pause the video here and give this problem a try. All right, test yourself, see how well you know things. Come back when you're ready to check. All right, let's take a look at the graph for this one. Okay, so let's take a look at what we know here. So here is your reduced form. There was a common factor of x plus 4, which means that, remember, the x-coordinate of this whole was negative 4 because that occurs at where x plus 4 equals 0. And subtracting 4 from both sides is what gave that x equals negative 4. Then the negative 1/5 comes from plugging in this negative 4 to the reduced function. So you're looking at that y value being 1 over negative 4 minus 1, and that's negative 4 plus negative 1, that's negative 1/5, or negative 0.2. You could write it that way too. Your vertical asymptote is at x equals 1, because that is where the denominator factor of x minus 1 in the reduced function is equal to 0. So we have that, which is right here. Your horizontal asymptote is a ratio of 1 over x, which tells you that you get y equals 0, your x-axis. And here I put a dashed line on the x-axis just to make it absolutely clear there. And so when we graph our whole, we have this point here. This did not look at the 0 or the y-intercept. Y-intercept would have been a good point. You probably got that one. It skipped here for some reason. The y-intercept is at 0, -1. But the hole that we have and the y-intercept are, once again, on the same piece of the curve. So we don't have a point for this piece over here. So that had to be calculated, and that's shown right here. Choosing the nice whole number of 2, plugging it into the reduced function, f of 2 gives us 1. And so that's that point right there, 2, 1. And then that allows us to finish up the graph. All right, let's take a look at this example. So I mentioned earlier in this lesson that not all of these, what we consider more complex functions, will have holes. And that's what we're looking at here. We have to realize, well, the binomials of 2x minus 5 and x plus 2, they can't be factored. They're prime binomial factors. There's no common factors to reduce, which means there's no hole, okay? And this is, of course, then the original function also is what we consider the reduced or simplest form of the function. It is as simple as we can make it. And so because there's no common factors that reduced out, there is no hole. So then I move on to my asymptotes. And for my asymptotes, again, my vertical asymptote, I'm looking at my denominator of x plus 2, where it's equal to 0. And that would be at -2. So x equals -2 is my vertical asymptote. My horizontal asymptote, I'm looking at y equals the ratio of the first terms from standard form, 2x over x. And that reduces to 2. So I get y equals 2 as my horizontal asymptote. Then I can look at the 0, which would give me 0 equals 2x minus 5 over x plus 2. Multiplying by x plus 2 gives me 0 equals 2x minus 5. Adding and dividing gives me an x value of 5/2 or 2.5. So that gives me the point 2.5, 0. And then my y-intercept would be f of 0, which would be 2 times 0 minus 5 over 0 plus 2, which would be -5 over 2, or -2.5. And so our y-intercept is 0, -2.5. And you're probably starting to wonder, is that a pattern? No, it's not a pattern. It is a coincidence. It's happened a couple of times that our 0 and our y-intercept have been opposite values, but I have to say that rational functions can get pretty funky, so yep, nope, not a pattern. Can't guarantee that's what's always going to happen. All right, so now looking at creating our graph, drawing our axes. X equals -2 is going to be on the left, y equals 2 is going to be above, so I can put this here, put this over here, and then graphing my asymptotes as dashed lines, of course. So x equals -2 will be here. Y equals +2 will be there. And we didn't have a hole, so that won't be helpful here. So I'm going to move on to my 0. Oops, that's not the right function. Let's try that again. So 2.5, 0, and that would be here. And 0, -2.5 would be here. Now be careful here. Make sure that your curve goes all the way through and towards those asymptotes at their locations. And again, those 2 points were on the same piece of the curve, so we will have to find a point over here for this side. So again, I would choose an x from this portion of my domain. Personally, I would choose the integer closest to that vertical asymptote, which in this case would be a -3. So I'm going to use x equals -3, so I'm going to find f of -3, and that is 2 times -3 minus 5, -3 plus 2. That gives me -11 over -1, which is 11. Now, this may or may not, that's the point -3, 11. That may or may not actually fit on my graph. Let's see, 2, this is 4, 6, 8. It does. It's like right at the top edge, so I could use it. But let's pretend that it doesn't. What do we do then? Don't put it up here and estimate. We've talked about how best practice is to make sure all your points are on your grid. Okay, so what you're going to do then is you are going to simply choose an x value a little smaller or over here a little bit further from -3. You just pick something else for x. Maybe you use -4 or -5. I'm going to try -5 or -6. They're kind of a little bit further out. They're probably going to move down a point down into here because remember this curve is going to come down. And so I'm going to, let's try -5 and see what happens. So I would try, okay, let's see what happens if x is -5. That's going to give me 2 times -5 minus 5 over -5 plus 2. That's -15 over -3, which is +5. So that gives me the point -5, 5. And 3, 4, there's -5, 2, 3, 4, right, and that's right there. And that's closer to the intersection of the asymptotes, which makes it a little easier often too to graph the curve. And then that will finish up that particular graph. All right, I have a practice problem for you to try here of this type. So again, pause your video, give this one a try, come back when you're ready to check. All right, let's take a look at the answer here, or the graph with all of its pieces and parts. So here, again, there's no hole. The function as it's given is in its simplest form. Vertical asymptote is x equals 1 because 1 minus 1 is 0, or because x minus 1 is equal to 0 at x equals 1. Horizontal asymptote, you're looking at y equals the ratio of those first terms in standard form, x and x, so x over x reduces to 1, and so y equals 1 is your horizontal asymptote. And this is using a slightly different strategy here. Let's see, this is, they call it the left side point, but this is also your 0 right here. And they call it the right side point, but let's see. Okay, yeah, this is the right side point where we had to choose a value. We chose x equals 2 in this case. And your y-intercept here, if you do f of 0, you should get 0 plus 3 over 0 minus 1, which is a ratio of -3. And that's what this point is right here, although the math isn't shown here. All right, that finishes up this particular lesson. You have a great day.